Hi, Ed LoRaDa here for my project submission for the Make with Ada 2019-2020 season. This project I've called LoRaDa. It's a follow-on to the work I had done a year ago for the previous Make with Ada contest. In that sense, it carries on with some of the BLE work that I did, but it further extends it into the domain of LoRa, long-range radio. So it's BLE plus LoRa together, combined in a fully Ada solution, and I will show you an interesting demo of this shortly. The genesis of this project came as we had problems with visitors coming into the garden. Cats would come in, do their business in our garden and then leave, or we've had some issues with squirrels climbing the sides of our house. So the idea would be that you would have some detectors, sensors that could be around the house itself, detect motion, and then allow a server to emit some form of countermeasure to address this concern. That's the genesis of the project. The question is, how do you realize it? So that's what I will show you, is the kind of tech you're going to need to address this type of problem. All right, let's look at a demo. Let's begin talking about the demo for my LoRaDa Make with Ada project. Now, in front of us, there are 7 boards, and each of them has a particular function in this demo. So I will go through and talk about each one. Now, the centerpiece of it is this board here. The STM32WB is underneath that can. Last year I demoed a sensor tile where it had a sort of a decoupled Bluetooth solution. They have a L476 talking to a Blue Energy module. Now, as of last year, they produced a single chip version of the BLE solution that has, basically it's an L4 CPU coupled with that Blue Energy module, but they talk together over a internal bus with hardware semaphores, and it's quite a different solution than an SPI bus. So a full Ada port was done to that target. Now, what's going on in there is not just the BLE, which will be talking to this cell phone, but also via these wires to the black box module here is connections over to the LoRa radio. So I programmed this BLE solution to be a BLE to the Android phone, and then be a LoRa server to the rest of the nodes that are in front of us. So we have a mix of nodes that make up the LoRa network. Everyone else, after that guy, the center, the WB55, everybody else is a client. He's the server, and then the rest of these are going to be clients. So we have the first LoRa board I got was these 2 red ones. They're from a company called Ronoff, and there was one of these crowd supply deals. And I was like, oh yeah, let me get one of those. And it was about $30 each board, unfortunately. They're quite expensive. And it looks like it's a single chip solution, but actually what's inside these large black chips there is actually 2 chips. And in fact, inside there is an STM32L073 and the Semtech SX1276 module. So it's one of these modules, basically. Well, it looks like a single chip. So I got these and got Ada working on that. And this is an older style ARM chip. It's an ARM V6. So it's a Cortex L0 Plus. And so, you know, that makes the code density is not great, but it worked out in the end, and we got LoRa working on that, a proof of concept. Then the next board I got was, there's got to be a cheaper way, and finally found these on eBay. These are the Heltec boards. They're you can sort of see the decoupled nature now, where you have the SX1276 decoupled from an STM32L151. So in this configuration, this is sort of the same thing as in this big black package, except they're broken out on the board. These are $14, and again, a relatively straightforward port of the same code base over to this target. And we have Ada runtime for these guys too, so that all worked out. And then back to my old favorite, I kind of like this. This is the blue pill, STM, it's a 10-year-old design, STM32L. It's an F103, sorry. Cortex M3, the usual 72 megahertz, only 20K of SRAM, so you have to be somewhat conscious of your SRAM usage.
And again, this one's connected to another LoRa radio, but this is this solution I've rather like. It's a black box, like the server. Each of these guys has a black box radio connected to it. So I think it's over an SPI bus, and you wire up the usual MISO, and the 2 interrupt signals, and it takes its 3-volt power, and there you go. You got a LoRa radio. So this solution's quite good. I mean, it's only it's like $9 basically, 6 plus the sub $2 blue pill board. So the most cost-effective the most cost-effective LoRa radio solution I could think of today, right now. And then finally we come to this one. Now, here's where I turned more gray, and this project basically got a lot more complicated with this board. This chip, basically this board came out sometime in November. And it looks like every other big Nucleo board with a 144-pin package. But actually this is a Cortex M33. So what that means is it runs trust zone. Actually, when you get the board from ST, trust zone is off. So it looks just like a regular, one of your regular big ST Nucleo boards. But once you turn trust zone on, this chip transforms. First, the demo that's on there doesn't work. So now you're stuck. You have no demo, you have no way of doing, and you have no way of really debugging this thing. So OpenOCD had reported to this, and that was a job in itself. So okay, so what exactly is a Cortex M33? It runs a secure domain and a non-secure domain on the same part. So you basically have 2 executables running out of the same flash. One's running securely and one's running non-securely. So that's how that works. Runs with 2 different images running on the same CPU. So each image has to sort of move over from one to the other, making calls to the non-secure side and the non-secure side back to the secure side. And the way I partitioned the work here was that I put basically all these client code here, I put the radio code over on the secure side. So what's actually talking to the radio is actually secure SPI. And then the actual client code, the stuff that actually does the LoRa packet analysis and sending it back and forth, is done on the non-secure side. So this is sort of like an interesting solution. It has sort of a security aspect to it, where you have like a high protected asset, the radio, and a non-secure application, which could screw up and will not take the chip down because the secure radio part is over on is protected against. You wouldn't be able to inject you couldn't make this be a different node because the node ID is over on the secure side. So the non-secure radio code cannot suddenly make itself be a different node in the network. There's some interesting applications, I think, for this type of technology. The secure boot is done in Ada, which then passes control over to the non-secure side. All right. Well, enough talking about this. Let's turn on this Android phone. And let's bring up this STBLE app. And we get our usual thing, connect to a device. So we search for it, and there's our device, LoRaDa, with my usual face feed MAC address. So we'll go and connect to it. Makes the connection. All right, we have a big LED grayed out, and we have a no alarm received. So let's turn on the LED. And magically you see all these LEDs come on. So each one of these has received a message over the LoRa net. The message was sent from the BLE phone to here, which then turned on its own LED, passed a message on across the LoRa network with retries, because you're never going to get this stuff through first time, not with this many nodes. So there's a retry mechanism going on. And finally all these guys got their messages, and there we go, all the LEDs come on. So now let's turn them all off. And one by one they wink out, out they go. Now, also we have a button. So if I press this button here, the blue user button on this board, button pressed with a timestamp. So the basic idea here is that what's going on is any one of these boards could send an event across to the server, which could then take action. Like I told you before, we have a creature problem, creatures coming into our garden. So the idea would be that one of these will detect motion and send the result of that over to this server, which would take an action to go and send back the LED, basically. Send back a message telling them to, take countermeasures. So that's how this works. This is basically a 7-node LoRa network and BLE server. So that's my project for the Make with Ada 2019-2020 project. It's the LoRaDa project. Okay, thank you very much.